Okay, this is Chapter 5, Part 2. And in Chapter 5, Part 2, we're going to focus on return measures and risk measures. Your textbook starts out first talking about a holding period return. Okay, a holding period could be any length. I mean, it could be a day, a week, a month, 5 years. But I will tell you, even though it is a single period, it becomes very difficult to start interpreting a holding period return when the holding period itself is not 1 year. For instance, if I said that you had a 1.7% return over the last 4 days, is that good? Or over the last week and a half, is that good? Well, somehow mentally you've got to figure out, 1.3% or 1.7. I wonder if that was good over 17 days, if that was the holding period. Well, what you'd need to do probably is convert that into a year, wouldn't you? You'd probably want to annualize it so you could decide whether or not it was a good return, or seemingly good. You'd still have to take into account risk. But the point here is that a holding period can be any length. I want you to notice something about the holding period return here. We've got PO, which is the value of the asset, the price, I guess, at the beginning of the holding period, and P1 is the price at the end of the holding period. So again, if your holding period was a 3-month holding period, that was the price at the beginning and the price at the end. D1 represents the dividend that was received during this holding period. All right. So what we see is that our holding period return really consists of 2 parts. It consists of this, which is really a capital gains percent, right? Where did our asset start? It started at PO, and it ended up at P1. So if I'm a portfolio manager, I'm hoping that was positive. Or if this is my own investment, I'm hoping that I had growth, positive growth. And if I take that positive growth and I divide it by my starting value, that gives me my capital gains yield. Either it was positive or negative. Certainly I'm hoping it's positive. In addition to that, if I received some cash flow during the time period, I had some type of income yield, right? If I received $3 and I started out and the price was 100, then I had a 3% income yield during that time period. So my holding period return is taking into account both my, let's see what that is. Is that an arrow? Sorry, there it is. Don't rush me, man. Yeah, that's not doing what I thought. It's taking into account my capital gains yield and my income yield and putting it together. All right, so we've got an example on the next slide here. The ending price was 110, the beginning price was 100, the dividend was 4, and so if we plug it into our model here, into our formula, we'd have 110 minus 100, so we had a $10 capital appreciation, we had $4 in income, and it started at 100, right? So that's 14 divided by 100, which gives us our 14% holding period return. I would caution you about evaluating that and saying, oh, that was good or that was not good, because a return by itself is, it's kind of meaningless. Other things held constant, we want our returns to be higher, but we don't know if it's good or bad until we take into account risk. And there's nothing here about the risk, is there? Okay. I want to work another one. Same type thing here. But this time it's going to be a margin example. We talked about margin in a previous chapter. Okay, I think it was chapter 3. So let's start here again. Let's say the beginning price is 100. The ending price is 110. Let's assume that this is a 1-year holding period. We're going to assume the following. Remember, on a margin, you have an initial margin and a maintenance margin. So our initial margin is going to be 60%. Now, what does that mean? Well, I bet you remember that the investor has to put up $60 in initial equity, which means $40 is the loan. They borrowed $40. Let me give you some more information in this example. I'm also going to assume, as we had before, a dividend of $4 was paid during the time period, and also the interest rate is 5%. Okay. The interest rate is 5%. So, what does that mean to us? Well, look, anytime you borrow money, right, we had a loan, we're going to be charged a 5% interest rate. That's what I'm telling you. All right. So I want us to calculate the holding period return for this investor on this investor's invested capital. Right? On this investor's invested capital. And so we're going to do the same thing. I'm going to write P1. That's what we had before. Minus P0. Plus the dividend that was received during the period. But if we borrowed money, we have to pay interest. So I'm going to subtract out the interest cost. Then in the denominator, I'm not going to put the initial price, but I'm going to put the, I don't have an abbreviation, I'm just going to say the invested capital. Okay. So this investor bought this asset for $100. At the end of the period, it was worth $110. This investor bought this asset on margin with a 60% initial margin. So this investor had to initially invest $60. So I'm going to put that in the denominator. That's all the investor took out of his or her pocket was $60 to buy this asset. The asset grew to $110, and it started at $100. So this investor has a $10 gain there. This investor received $4 in dividends. But this investor also has to pay interest. The loan amount was $40. If we multiply that times 5%, I think that's a $2 interest cost on that $40 loan. So we have 110 minus 100 plus 4 minus 2. If I'm doing my math correct, I believe that is 12 divided by 60, which is 20%. Let's compare that to the previous slide. If you remember, no margin, we had 110 minus 100 plus 4 divided by 100, which gave us a 14% return. What we did was we bought this stock on margin, and because we did, the stock price increased. We had leverage, didn't we? And we were able to increase the return. We did increase the return on our invested capital from 14% to 20% through the use of margin. Okay, next few things we have. We've got expected returns and standard deviation. This is not really a hard concept. What's hard, or what kind of makes this harder for students, is that there's a lot of notation here. This is really kind of a weighted average is what we're going to see here. It's really a weighted average. What we're saying is we've got probabilities. So PS is the probability of something occurring. So it might be the probability of a recession, the probability of just an average economy, the probability of a boom. Okay, so that's this first part. That's the probability of something happening. And the second part is the return if it does happen. And so what we're going to do is, and we'll see this on this next slide here, there's a probability that next period we're going to be very happy, an excellent economy. There's a 25% chance. And if that happens, we believe that the rate of return is going to be 31%. There's a 45% chance that there's just going to be a good market. And if the market is good, we'll earn 14%. There's a 25% chance that it's going to be a poor market. And if it is, we're going to probably have a negative 6.75% return. And there's even a chance of a crash. There's a very low probability, but 5%. And if we do have a crash, we're going to lose 50% of our value. So we're able to take these probabilities, and by the way, these all add up to 100%. Right? We don't know what's going to happen, but that's the probabilities of what we think will happen. So we take our first 25% chance of an excellent economy and multiply that times the return if that does happen. We're going to add that to the second scenario, 45% chance of earning 14. There's a 25% chance of losing 6.75. So each one of these, we multiply the probabilities times the return should that event occur, and we basically add it together, and we get an overall average of 9.76%. That's the average, 9.76%, taking into account probabilities. In fact, we'd say if this happened over and over and over and over again, and we repeated each one of these, next period multiple times, we would expect long-term that the average would be 9.76%. Now, how about the variance and the standard deviation of those returns? Well, again, this is a formula that it looks kind of scary, okay? But it's some of the same information that we had before. Here's the probability. That's the probability of an excellent economy or a good economy or a poor economy or a crash. This is the rate of return should that event occur, should that state of the world occur. But in brackets here, if you'll notice, what we're doing is taking each one of those returns, the return for an excellent economy, and we're going to subtract that average that we just came up with, the 9.76%. So we do that. We take the return in the state of, whatever that probability was, the excellent economy. Take the return in an excellent economy minus the average for all of them. Take that deviation, and we square that deviation, and then we multiply all of that times the probability. Then we do the same thing for the good economy. We're going to see this on the next slide, I believe. Yes, we do. And so when we do all that, we get the variance. When you take the square root of the variance, it gives you the standard deviation. So here's our example. If there was an excellent economy, there's a 31% return we're expecting. We subtract that average, 9.76. We square that deviation and multiply times the probability. Okay? We do the same thing for a good economy. Remember, there's a 45% chance of a good economy. In a good economy, we would expect to earn 14%. We take that 14, we subtract the mean, the average of all of them. Our formula says to square that deviation. So we take what's in the parentheses, squared deviation, multiply it times 0.45. Remember, there was a chance of a poor economy, a 25% chance. In a poor economy, we would lose 6.75%. Again, we subtract the average that we calculated, square that deviation, and multiply that squared deviation, multiply what's in parentheses, times the 25%. Okay, finally, if in fact there is a crash, we're going to lose 52%. We subtract from that 52% the average. We square that deviation and multiply it times the probability of a crash. And when we sum all those together, because we have lots of equal signs and or addition signs, don't we? We add all those together. That gives us our variance. When we take the square root of the variance, we get the standard deviation. So I'm going to go back a few slides so I can point something out here. Here we go. And this is our expected return and standard deviation. All right? We're expecting it. We're forecasting. That's another name. Forecasted returns. Forecasted standard deviation. Right? Because we don't know what's going to happen. We've got probabilities of something happening. We've got a 25% chance, a 45% chance of this, a 25, a 5. We don't know what's going to happen, so these are forecast. We're using probabilities to say, okay, we don't know what's going to happen. All in all, this is my expected return. This is my expected standard deviation. Well, these next slides, I think, take us to something a little bit easier. This is a time series analysis of past rates of return. Well, because they're in the past, we're not forecasting them, are we? In fact, we know they've occurred. We know they've occurred. They've occurred with equal probability. I mean, they've all occurred. This, if you'll look at, there's that probability again, right? We used that a moment ago with a 45% chance, a 25% chance of those different returns. That's not what we're doing here. If you'll notice, we're going to take all of those and divide by n, where n is the number of observations that we have. There's nothing to forecast. It's already happened. So what we're going to do is average. We're going to average. This is the arithmetic average of the rates of return. Let me give you an example here. What if I told you this is what has happened the past several periods? 10%, 15%, 3%, 12%. Right? The last 4 periods, 10, 15, 3, and 12. Well, if I ask you to calculate the average, you would know what to do. We've been doing that since middle school, grade school, whatever. 10 plus 15 plus 3 plus 12, all that sums to 40. And so if we take 40 and we divide by 4, because there are 4 observations, we get an arithmetic mean of 10%. That's all we're doing on this page. It's the arithmetic average. It's an arithmetic average. Let me show you something that's the problem with an arithmetic average. Returns don't grow arithmetically. Okay? Year 1, year 2, year 3. Here are 2 different assets. XYZ and ABC. Let's say that this first one, here are the returns. Man, they were volatile. This one lost 60%. This one, the next year it gained 40%, and the next year it gained 80%. Whereas this one earned 5 and 5 and 5. Okay. Well, if I were to calculate the arithmetic mean, I'm going to add up all the returns over the last 3 years for XYZ. That's negative 60 plus 40. That's negative 20 plus 80. That's 60. So 60 divided by 3, the average is 20%. Whereas with ABC, the average was 5%. Well, here's the problem. You can't look at and you can't decide and assume that XYZ was better than ABC. Right? Even if you were to ignore risk, you can't. Because if you started with $100 in each one of these assets, let's see how much you have with ABC. At the end of the first year, you would have earned 5%, so now you've got 105. At the end of the second year, you earned 5% again, but this time you earned interest on the interest. You compounded, so it's actually 110.25. And then you earn 5% again. It's actually 115.7625. So $100 would have grown to almost 116. On XYZ, you lost 60% the first year. So if you had $100 invested and you lost 60%, at the end of the first year, you've got $40. Good news is you started to rebound. you earned 40% rate of return in year 2, but you only had $40 invested. So that's that's a $16 gain. So now you're at 56. And then you had an 80% gain. That's great, but you had $56 invested. That's $44.80 you earned. It would have grown all the way from $100 to $100.80. So it should be clear to you that you would have been better off in ABC because your money, your $100, would have grown to a much larger value. So what's my point? My point is that the arithmetic mean that we just calculated, that's fine. We need it for a few things. But returns don't grow that way. Returns don't grow arithmetically. They grow geometrically, which is why the next slide takes us from arithmetic to geometric. Our geometric average return. Now again, this looks a little more complicated than it has to be. But let me remind you, excuse me, my example, 10%, 15, 3, and 12. Okay? So let's take just any dollar amount. In fact, I'll just make it $1. If I earn 10% the first year, I'm just basically going to say 1 plus my interest rate. 1 plus 10%. I've got $1.10. And then I multiply that times 1 plus the rate for the second period. Basically, I'm allowing my $1.10 now to grow at 15%. I'll multiply that times 1.03 because now whatever that value is, it's going to compound and grow at 3%. Multiply that value times 1.12. And what you'll find is you end up with 1.4593. So if you start with $1, then 4 periods later, you've got $1.46 almost. Okay. Well, our formula for geometric mean is to take this terminal value that you've just calculated by, 1 plus the rate times 1 plus the rate times 1 plus the rate. 1.4593. Raise that to the 1 over n power. Well, we had 4 n's, or 4 observations. So I'm going to raise that to the 1/4 power and subtract 1. And what I'm going to end up with is 0.0991, which is 9.91%. So I'd basically 1.4593, raise that to the 0.25 power, and subtract 1. You can do that on your calculators, on your financial calculators, using your y to the x key. Another way that you could do this if you wanted to, I'm going to come over on the left-hand side of your slide. We're basically saying if you had invested $1, it's going to grow to 1.4593. So you could enter in a -1 in your calculator if you have a financial calculator. Enter in a -1 as the present value because you would have to invest $1, which would be a negative cash flow. Then plug in 1.4593 is the future value. And then plug in 4 is in because it was 4 returns, and then solve for I in your financial calculators if you have them. And you would get 9.91%. So that's the geometric mean and the arithmetic mean. The next thing we see here is variance in standard deviation. Okay. Again, I find this to be easier. than using the probabilities. It's the same kind of concept. Again, except we don't have to take into account probabilities because all have occurred. All of the returns actually did occur with equal probability. So we don't have to multiply times probability. We'll simply calculate what's in brackets and divide it by n. That is, take the average right? Why don't we, let's do the one I just did a moment ago. 10, 15, 3, and 12. Okay? Our formula, and if you recall, the arithmetic mean, I'm going to call that, I guess I'll call it R bar. Our arithmetic mean that we calculated a moment ago, arithmetic mean was 10. 10 plus 15 plus 3 plus 12 divided by 4 was 10. So what our formula says to do is says take each one of the returns that we have up here, 10, 15, 3, and 12, and subtract the mean. Take each one individually, subtract the mean, square that deviation. Do it for each one of them. Our summation side says then add all of those squared deviations. And then this multiplying it times 1 over n is the same as just saying, and now take the average. Let's look at it on this page here where I've got more room. Okay, so we had 10, 15, 3, and 12, and our mean was 10. Our formula, I'll write that down for you, says 1 over n, sum s equals 1 to n, rs minus r bar squared. So let's take each one of our returns. We had 10 first. And let's subtract the mean, which was 10. And then we have to square it. Let's add that to the next one. The next one was 15 minus the mean, which is 10, squared. The next one is 3 minus 10, squared. The next one is 12 minus 3, squared. Okay? So we've done everything except the 1 over n. We can multiply all of that times 1 over n, which is the same as dividing by n. So 10, let's work the first one here. We've got 10 minus 10. Well, that's 0. Right? 15 minus 10 is 5. 5 times 5 is 25. 3 minus 10 is negative 7. Negative 7 times negative 7 is 49. Oops, I've got a mistake here. Ooh, don't you hate it when that happens? We also have the last one, which was 12 minus the mean, which was 10, which is 2, and 2 times 2 is 4. All that divided by, there were 4 observations. I think I can do a better job on drawing a line. A little bit. Okay? So I have 29 plus 49. I believe that is 78. 78 divided by 4. Let's see if that is in fact what that is. 29, 49, 4 divided. I get 19.5. So 19.5 is my variance. If I take the square root of the variance, I get standard deviation. So the square root of 19.5 is 4.416. And so the standard deviation is 4.416. Okay. Now our next slide says, when eliminating the bias, variance and standard deviation become. Okay. So let me put this into some other terminology that perhaps you've heard of before. Perhaps you've heard of the sample standard deviation and the population standard deviation. Okay. Well, what we just did a moment ago, where we've got this RS minus R bar squared sum S equals 1 to n. If we multiply that times 1 over n, this was giving us the population variance. And then the square root of that would give us the population standard deviation. When you use n minus 1 in its place, so I could have the same thing, this RS minus R bar squared, the sum, S equals 1 to n. And I'm going to multiply that times 1 over n minus 1. This gives me the sample variance. And if I take this square root of the sample variance, I get the sample standard deviation. So that's what it's talking about here. So it's not a big ticket item. I don't want you to worry about it. If I wanted you to use the population, I'd tell you that. If I want you to use the sample, I'd tell you that. But the only difference between the formulas, between using the population versus the sample, is that the population uses n, and the sample uses n minus 1. So like I said, it's really not a big ticket item. Now, this next term here is the Sharpe ratio. And the Sharpe ratio is a measure of risk-adjusted returns. What we've got in the numerator here is the risk premium. And the risk premium, again, this is for a portfolio. So let's define R sub P to be the portfolio return over a certain time period. Maybe over the last quarter, right? That was your portfolio return. Let's define R sub F to be the risk-free rate. It's what you could have earned on a T-bill, for instance. So RP, which is what you earned on your portfolio, minus RF, which was the risk-free rate, is what's referred to as the excess return, or as it has up here, the risk premium. Okay, that's what's in the numerator. The numerator has the return on your portfolio during the time period minus the risk-free rate. Now, as a portfolio manager, you're certainly hoping that's positive, right? You're hoping that you earned more than the risk-free rate, because if you didn't, like, you could have, why did you waste everyone's time and money? Because you could have invested in a risk-free security and earned more than you actually earned. So as a portfolio manager, certainly we're hoping that's a positive number. But just because you have a positive return, and even a positive excess return, doesn't mean that it was a risk-adjusted return, right? What we need to do is say, okay, that's what we have. What we know we have in the numerator is the return. But how much risk did this portfolio manager expose us to in generating that return? And so that's where we look at the standard deviation, because standard deviation is a measure of risk. How much did our returns deviate on average from what we expected it to be? How much were those deviations? The greater the deviation, man, the more volatility, the more variation, the more risk that we were exposed to. So we do have in the numerator, I wish that didn't say risk premium in the numerator, and I know that's really what it is, but I prefer that it says excess return, because that's what we've got in the numerator, is return. We've got excess return in the numerator. And in the denominator, we've got some measure of risk. So it's excess return over risk. Since this is a measure of portfolio performance, we want this number to be higher. There's two things that would make this ratio higher. Either the numerator is higher, which is good because we earned a higher excess return, and or the denominator is lower, meaning that we did it and we really didn't have as much risk. There was not very much volatility. Now, standard deviation is kind of universally accepted in many levels, I should say, as a measure of risk. And one of the reasons that we're able to do that, and it makes it easier, is when we assume normality. When we assume that the returns follow a normal distribution. And I'll remind you of what that is, I think, yes, on the next slide here. A bell-shaped curve. But if our returns are normally distributed and follow a normal distribution, then standard deviation is a pretty good measure of risk. Okay? And we like that because there's some great properties of a normal distribution. I don't know if you remember this from a statistics course, but if you've got, right here, if you've got a distribution that's normal, right here in the middle of your distribution here is your mean. So this is a normal distribution with a mean of 10 and a standard deviation of 20. So here's R bar right here. That's your mean. Okay. If we go one standard deviation away from the mean, and remember standard deviation is 20%. So if we start here at 10 and we go one standard deviation away, that takes us to 30. That's plus one standard deviation. And if we start at 10 and we go to the left by 20%, it would take us to negative 10. Well, that's significant because of what we know about statistics, and I believe it's the central limit theorem that helps us know that approximately 68% of the area under the curve is really within one standard deviation of the mean, of the middle. So we could interpret that and say there's a 68% chance that this return is going to fall anywhere from negative 10% all the way to positive 30. There's a 68.2% chance. Right? There's about a 95% chance if we go two standard deviations out. And then 99%, we got 99.7. But, at least 99% of the area under the curve is within 3 standard deviations of the mean. See, that's pretty useful, right? Because now we can really quantify our risk. We can say, well, I don't know what's going to happen next period, but based upon historical values, based upon historical returns and the fact that our returns are normally distributed, I've got a pretty good estimation as to what my risk levels are. I've got a pretty good estimation of that I could lose. In fact, here's my question to you. What is the probability of a loss greater than 10%? What is the probability of a loss greater than 10%? Well, let's do that. Here's 10% right here, a negative 10%. And we know that from this point to this point is 68% approximately. I'm just going to approximately do this. Okay? So if about 68% is within one standard deviation, and there's 100% under the curve, then there's about 32% that lies outside of that. Okay, so if 68 is within that range, then 32% is not in that range. And since we're symmetric about the mean, about 16%, there's about a 16% area over here that falls to the left of that one standard deviation. So that answers my question. I say to you, what's the probability of a loss that's greater than 10%? I don't want to, greater than a loss, I said. So what's the probability that I'll lose more than 10%? About 16%. So again, these statistics here, one standard deviation at about 65%, 2 standard deviations, about 95%, 3 standard deviations, about 99%. That only holds if the distribution is normal, if the returns follow a normal distribution. So what happens if they don't? Well, we've got some more statistical problems. We'd have to, if the excess returns are not normally distributed, then now we're going to say, well, standard deviation might not be a good complete measure of risk. If standard deviation is not a good measure of risk, guess what? The Sharpe ratio is not really a good measure of portfolio performance. Because if your standard deviation is not capturing all the risks, then you're not really measuring risk-adjusted returns. Okay, what would cause something to a return to basically to not be normal? Well, often we'll find these two things at play. One is called skewness, and one is called kurtosis. A skewed distribution. Let's see, they're just showing us how to measure skewness and kurtosis. It's what we call the third moment of the distribution and the fourth moment of the distribution. I'm not too concerned about. This is not a statistics class. I would rather you see what skewness is. If a distribution is skewed, let's take the black line here. Okay, I'm gonna mark it in red though. The black line, I'll tell you what, let's start with our normal distribution. Let's see, which one is that? It's hard for me to even see here. I've got positively skewed, okay, negatively skewed. So I think it's our light line. So this is our normal distribution. All right, in red. I want you to look at the black line now. The black line is not normal. In fact, I'm highlighting in yellow. Look how it's skewed over. There's more. It leans out. That's not very good. Let's go to my note page here, and I'll do my best. Okay, I said I'd do my best. That's my attempt at a normal distribution. Okay, we're symmetric about the mean. All right, now let's try to do one that's not normal, but that's skewed to the right. Oh, good night. That's a distribution that's skewed to the right, positively skewed. Okay, skewed to the left. You can imagine what that would look like. It would be more like not very good. But we've got normal. We've got skewed to the right. Skewed to the left. Okay, so again, I probably should have left this one alone, but you can find in here a positively skewed, a negatively skewed, and a normal distribution. You can also see a distribution that is affected by kurtosis, and kurtosis has to do with when you look at the tails, look at the fatness of the tails. If you look at our, I don't want to mess up the beautiful slide here, but if you'll notice the gray, which now I am messing up, I'm putting red dots on it, that's a normal distribution. Okay, and the normal distribution comes down here. Look at the blue line. The blue line is skinnier in the middle, but it's got fat tails, doesn't it? See these fat tails out here? They're taller, they're fatter. And so kurtosis has to do with the fatness of the tails. Both skewness and kurtosis are deviations from normality. And so if we have a skewed distribution, or if we have a fat-tailed distribution, then those great statistics that we talked about earlier, the 68, the 95, the 99, they're just not going to hold. Those are not good complete measures of risk. Standard deviation is not a good complete measure of risk under those scenarios, and as such, our Sharpe measure is not a good measure of portfolio return.